You know, we're surrounded by stuff we use every single day, but might not really understand. Today, we're going to tackle one of the most common ones, the humble electrical outlet. It's this gateway to, well, basically limitless power, right? But what's really going on inside? All right, so let's get right into it. You've seen this on pretty much every charger you own, 230 volts, 120 volts, AC. But what does that AC part actually mean for you and your devices? Let's unplug that mystery.
So, to really get what's coming out of your wall, you first have to understand a pretty basic thing. Electricity isn't just, well, electricity. It actually comes in two totally different flavors.
First up, you've got direct current, or DC. Just think of it like a river, The water flows steadily, always in one direction. That's the kind of power you get from batteries. But then you've got alternating current, or AC, and this is a whole different beast. Here, the electrons are more like the tide, constantly switching direction, flowing back and forth, and that is what's powering your home.
Okay, so we know our homes run on that back and forth AC stuff. But before we get into the why it works, we really need to nail down what we even mean when we say electric current.
Look, at its heart, electric current is just charges on the move. That's it. Picture this. Inside any metal wire, you've got billions and billions of free electrons just bouncing around like crazy, totally random. But the second you apply a voltage, that's the push, it organizes that chaos. Suddenly, they all start moving in the same general direction. And that collective organized flow, that is what we call current.
And we can even dig a little deeper and think about how concentrated that flow is, right? It's like taking that same river of electrons and squeezing it through a much narrower pipe. The flow gets way more intense, more concentrated, and that intensity, that's the key to how electricity actually gets work done.
Now get ready for this, because it's going to sound a little weird. Even though those electrons are all getting pushed in one direction, they're still bouncing around like pinballs. Their actual forward progress, what scientists call drift velocity, is unbelievably slow, like we're talking millimeters per second. So how does your light turn on instantly? Well, it's not the electrons racing to the bulb, it's the push, that electric field that travels at nearly the speed of light. It's the signal, not the messengers, that's fast.
So we've got this flow of charge, but how does it all connect? The push from the voltage, the flow of the current, and even the wire itself, how do they all relate? Well, it turns out there's one beautifully simple rule that ties it all together.
And here it is, Ohm's law. It's the super simple but crazy powerful equation. V equals I times R. Voltage equals current times resistance. The easiest way to think about it is like this. How much water flows through a hose? That's the current. Depends on how hard you turn on the tap, the voltage, and how narrow or kinked the hose is, the resistance. Simple, right? And don't let that simplicity fool you. This one little relationship is the absolute bedrock of, well, everything electrical. From the tiny circuits in your smartphone to the massive power grid that lights up a whole city, engineers are using this fundamental law to design, analyze, and control it all.
Okay, we've got our fundamentals down. Now let's circle back to the big puzzle we started with, that weird alternating current that's in our walls.
So an AC signal, especially the nice smooth sine wave that comes out of our outlets, is perfectly balanced. It's symmetrical. The amount of time and energy it spends flowing in one direction, which we can call positive, is a perfect mirror image of the time and energy it spends flowing in the other, negative direction. So, with that in mind, if you were to average it all out over one complete back and forth cycle, what do you think you'd get? What's the net result if you take one big step forward and then one big step right back to where you started?
Yep, you get zero, a big fat nothing. The positive part and the negative part completely cancel each other out. From a purely mathematical standpoint, the average value of a true AC current is zero.
And that should really make you scratch your head. This is the big question, right? If the average flow is zero, if the electrons don't really go anywhere in the long run, how in the world is your TV turning on? How is any power getting delivered to anything at all?
The whole solution lies in a really clever trick, a different way of looking at it. Instead of trying to measure the average flow, we're going to measure the effective power. And we do that using something called the RMS value.
Okay, so this is the crucial takeaway. RMS stands for root mean square, but don't worry about the math. Here's what it means. It's not about the average direction of the flow, because we know that's zero. It's about the average effect. The RMS value answers a simple question. If I wanted to get the same amount of power, the same amount of heat from a toaster, for example, what DC voltage would I need? It's a way to compare apples to apples, measuring the real useful energy that's being delivered. That's what actually matters.
And you can see the difference laid out perfectly right here. When it comes to calculating power, the average value is totally useless. It's 0. But the RMS value, that's the gold standard. It tells you the actual work-doing capability of that AC signal.
And that brings us all the way back to the beginning. That number printed on your wall outlet, whether it's 120 volts or 230 volts, what is it? That is the RMS value. It's not the peak voltage, it's not the average voltage, it's the effective power delivering value. It's telling you that your outlet delivers the same punch as a 120 or 230 volt battery would. Mystery solved?
So we've cracked the code on the wall outlet. But you know what? The story of those moving electrons doesn't stop there. Because it turns out, anytime you have electricity in motion, something else magical happens. A whole other force comes into play.
There's this fundamental law in physics, the Biot-Savart law, which basically says that any wire with a current flowing through it instantly creates a magnetic field all around it. It's not a sometimes thing, it's an always thing. Moving electricity and magnetism are, well, they're inseparable.
Here's a good way to think about it. You know how charges that are just sitting still will push or pull on each other with an electric force? Well, the moment those charges start moving, they create this whole other kind of force, magnetism. They really are just two sides of the very same coin. And this deep, incredible connection, electromagnetism, is, and I mean this literally, what powers our entire modern world. The way we generate electricity in power plants, we use magnetism to move electrons. And the way every electric motor works, from a fan to an electric car, we use those electrons to create magnetism that makes things spin. It's this beautiful two-way street that basically runs everything. So think about that. We've gone from a simple plug on the wall all the way down to the fundamental forces that built our civilization. We've figured out how to wrangle these impossibly tiny electrons and get them to do amazing things for us. Which just leaves one final big question. What's next? What's the next great leap in energy that's going to change the world all over again?